Hello and welcome to this presentation on calibrating a collection system model. My name is Tom Walski. This presentation is going to be not so much about which button do I push on the computer to get the model to calibrate, because there is no button that says calibrate my model. Okay, instead it's going to be more like Zen in the art of model calibration. How to approach these problems and what kind of tools you have to solve them. Calibration itself consists of comparing what you observe in the field to what the model tells you and adjusting the model or throwing out bad field data so that the model and the field data are in agreement. And this is an iterative process, and theoretically it's pretty simple. You find out what the problem is and fix it. Okay, it's devil's in the details though. But let's talk about why we're doing this. We're going to be asking the question of why a lot during this, because calibration is time consuming. It's a lot easier to sit in your office and build a model than it is to go out and get all this flow data in sewer systems. But these decisions you're making are going to involve millions of dollars. So isn't it better to, understand what you're doing, have a really good decision support tool, which is what models are, and the calibration will pay for itself in cost savings and more efficiency in your system. And accurate models then lead to good decisions. And they also give you some real insights into the system. When you're getting this data and looking at it, you start to realize why certain things are the way they are. And in general, they'll build confidence in the model, your confidence and the confidence in the people that you work with and use that model for decision support. So there's some good reason to do the model calibration exercise. And overall, it also establishes teamwork, because a modeler just can't sit alone in a room and do model calibration. It's really a joint effort of the people in engineering and operations and maintenance collecting the data, massaging it, looking at why are things not agreeing, what's going on in this part of the system. So there's a lot of teamwork in doing model calibration. It's not a one-person operation. Now, calibration really involves two fundamental steps you saw in that first slide. The first one is if there are differences between the model and the field data, why are they different? And this is the hard step. This is the one that really requires you to think. And then the second step also requires some thinking, but it's a lot easier. It's fix the problem. Okay, so once you figure out where the problem is, fixing it is the relative easier step of the two. And if you read journal articles about model calibration, they'll always focus on the second one, and that first one is really where the work is. Okay, so calibration is not like, remember old television sets when you turn them on in color TV and the grass would be purple and the person's faces would be green, and you'd have a whole bunch of knobs to turn to figure out how to make things agree. And that's what calibration is a lot like, but now you have many, many knobs to turn. You have all kinds of parameters that you could adjust to get better calibration. And if you don't approach it in a logical way with good data, you can be very frustrated and try to calibrate a model with any quality. Because we have a lot of things we can adjust to make a model calibrated. You could start with the dry weather loading. Now we're talking here about stormwater models, sanitary sewer models, combined sewer models. What I'm talking about covers across all those types of models. So some of them, like dry weather loading in a stormwater system, is pretty trivial. There's no flow. But in some of them there is a dry weather flow if you have a sanitary component. Pipe roughness, elevations could be wrong, manhole losses could be wrong, there could be blockages, the catchments that you delineated to calculate the inflows could be wrong, your precipitation data could have problems. If you're a pump system, you have problems with the pump and with the pump properties that you got to enter, or your field data could just be wrong. People have been trying to calibrate models to match incorrect field data for years. And it's a frustrating thing when you get stuck in that situation. So there's a lot of things you can adjust. And this is why you've got to figure out, why is the model not agreeing with the field data? And this is where you can then focus in on one of these 5 or 10 things that you've got here. Okay, so really there's several different kinds of calibration. There's the dry weather flow calibration, which for sanitary sewers is important. For combined and especially storm sewers, not very. But then you have separate sanitary systems where you've got one type of approach you can use because you don't know how the wet weather flow is getting in there. And then you have combined sewer systems and stormwater systems. There's a lot of different approaches for different kinds of problems. Now, the most fundamental question you need to ask, I said we're going to be asking about why a lot in this talk. And one of the next fundamental questions is, why are you building this model? Because the use of the model will determine to a great extent how you go about calibrating it. If you're building it for a master planning study, you need to focus on the big pipes, the big elements, and you don't worry too much about the little sewers up in the fringe of the system because they aren't going to matter that much in this case. Or if it's a stormwater system, the individual inlets and gutters, you don't pay that much attention on it. On the other hand, if this is for system expansion, where you're going to be adding a new subdivision or adding a new industrial park or something, here the little pipes out the fringe, the places where you're going to tie in the new growth, become very important. And it's not just the big pipes, it's those little pipes or the pipes that you're going to connect into that become really important. Or is a study done for regulatory enforcement? You're under a consent order that you have to fix overflows by a certain date. Well, in this case, you're really going to focus on those big pipes that are overflowing. It doesn't matter what's going on way up in the top of the drainage basin so much as what's going on in the areas where they have overflows or the area that causes the overflows, really. Or it could be real-time control. And here again, you're focusing more on the bigger pipes or the things you can control. So while you're building the model has an effect on what you do for model calibration. Okay, so let's go through now the steps in going through all of this. First thing you do when you start this kind of analysis is see what kind of data is out there. Okay, it seems pretty simple. Make sure you did an exhaustive study of what's available. Some data that you almost always have are the flows of the treatment plants or outfalls. Pump station operation records. They usually go into the SCADA system. There's some type of logging of the data, so you have that kind of data. Wet well levels are also something that's generally logged, so you have this kind of data. You don't have to go out and do extra work. And you also have data on the dry weather flows. If this is a system that accepts sanitary waste as well, then you have customer water meters that provide you a lot of insight into where the water is coming from. So gather up this kind of data and evaluate what's going on. And this is stuff that should be at your fingertips. Okay, but that's usually not enough, right? You need to go out and get data. And there's two parts to this, is how do you collect it and what do you collect? One of the first choices is, do you install permanent flow metering equipment and pressure measurement equipment and permanent things, or do you have portable devices that you can install for the duration of a study and then remove it? And then what do you measure? Well, usually the main things you measure in the pipes, in the buried infrastructure, are flow level, and the thing on the ground is rainfall. And so these are the things that you need to be sure you get data, because usually there isn't enough of this kind of data. You usually say, gee, I wish we had a flow meter at this point, or I wish we had some rainfall data in this part of town. So these are the ones you're generally going to have to do something about. That's not going to be enough available off the shelf. So let's look at some simple things you can do. This is now the real quick and dirty old-fashioned kind of stuff. You want to know what the flow is into a wet well? Well, you turn the pump off and see how long it takes to fill at a certain level. You want to know the flow in the sewer. You could put some type of dye or a salt in there and see how long it takes for that to move downstream. You can use just a velocity probe where you could stand on top of the ground with that long handle and stick a velocity probe in the sewer to get an idea of the velocity. Then there's things to figure out. Are manholes flooding? And there's some techniques where you just basically put a chalk mark inside the manhole before the rain, and you go back afterwards and see how much that chalk was erased. And that'll tell you how far the water backed up into the manhole. Or you could hang cups, a series of cups from the side, and see which cups are full after a rainfall event. You get an idea of which manholes are getting surcharged. You don't have to be out there in the middle of the biggest storm to try to catch this sort of thing. So those are just some simple things that you can do with a minimum of technology. But let's get into the more fun stuff. Well, there's control sections. A control section is a feature that produces this one-to-one relationship between depth and discharge. And Weirs and Flumes are places that you could have that relationship. The key thing to measure here, therefore, is the water level. And there's a lot of really good technology out there nowadays that you can get good values. So it's these devices that measure level are the key to these calculations. And there's, like I said, many of them, you don't need to stick a ruler into the sewer to figure out these things. There's a lot of ways of doing things a lot better. Okay, so let's look at some of these control sections, see when they work very well. Okay, weirs are okay. Sharp-crested weirs, though, tend to get sediment behind them. So they're okay for temporary flow metering, not really that great of a long-term solution. On the other hand, if you have outfalls, like combined sewer overflows or stormwater discharges, broad-crested weirs generally tend to be better for those kind of cases, and they're more of a permanent thing. And portable, weirs are okay, especially when there's pipes you're worried about that have a very low flow. Of course, if you have very low flow, they're probably not the pipes that you're really all that interested in. The other type of device, the kind that I like the most, are flumes. Okay, partial flumes like this one here, which is not a good one because it has a lot of waves in it, but the partial flumes are the most common and tremendously reliable. They get the area from the depth of flow, and it's really, the accuracy is only limited by how well you can measure the depth. And it's got a tremendously wide range. Among the flow metering devices you have, this thing here can measure like, a turn down of 100 from the highest they can measure down to the lowest. They're really good. The problem is they're expensive to install, and if they aren't out there already, you're probably not going to be able to install one in a sewer system. But if you do have the option, so for example, a major overflow from a stormwater system into a stream, you might be able to do something like this, as long as you don't have the backup from downstream. And these things are just, really, they're kind of bulletproof flumes like this. Okay, but generally what you end up doing are in-pipe measurements. Okay, so in this case, you have to measure velocity and depth. And these could be permanent meters, they could be temporary meters. And the math behind this is pretty simple. Q equal AV, which is something we learned early in fluid mechanics, so that's not too hard. But you really should have systems where both of the sensors work. Okay, and sometimes one of them can fail. And if it's in a range where you have a lot of historical data about the relationship between velocity and depth, you could do some correlations. Of course, if most of your data was collected and your correlations based on depth between a quarter full and half full, and now you're trying to measure the relationship when it's 80% full, it may not be as accurate. But there are some things you get by with if temporarily you kind of lose one of those two sensors. But really, you need the two sensors for these types of devices to work. So, flow measurement techniques depends on what kind of range of expected flows you are, where you're working. You just have to assess the situation. Control sections are good, but they're expensive to put into a system. And you got to watch out that they can't back up. You can't have the weir get submerged or flumes submerged. And so what you end up doing in most studies, if you're doing it for a client, if you're a consultant, is use these portable velocity area measurements. They're good systems, and they're not quite as reliable as, say, a partial flume, but they're still quite good, and they've been around for long enough that we know a lot about them. And maybe 5-10% accuracy. The manufacturer will claim a higher value possibly because they do their testing in controlled conditions, and sewers are anything but a controlled condition. Okay, the next kind of data you need is precipitation data, because you can't do much with the model without knowing the wet weather flow. So you can always go out there and have somebody during a rainfall event go out there every 10 minutes and read the gauge, but that's not a lot of fun. So you usually use some kind of recording gauge, and there's a lot of different technologies out there, which we're not going to get into the details of, but there's a lot of ways to measure these things. And nowadays, we're also getting some really good data from radar, and you can get that kind of data fairly readily nowadays, which is a big plus. You got to be careful what kind of rainfall event you're dealing with, though, because when you try to calibrate the model, you'd like the rainfall over a given catchment or subcatchment to be fairly uniform. And that usually happens when you have these big frontal rains coming through, not these isolated thunderstorms. Because I'm sure you've been out sometimes where you'll be driving through just a terrible torrential downpour, and then a mile later, the sun is shining and the pavement's dry. Because these isolated thunderstorms can really be variable, and they could play havoc in your model calibration. So you'd like to, the extent possible, rely on big frontal rains where this whole area be a kind of a uniform shade of green as opposed to these spot thunderstorms. Because what usually happens with me is when I want to do some flow metering like this, we go into a drought and you don't get any rainfall data, and then you're really stuck. So hopefully when you put your flow metering and your rain gauges out there, you get some really nice rains. So good luck with that. One thing though that you got to worry about is if you're getting data, question the data. Sometimes you get data just inconsistent. It just doesn't make sense. How could the wet well be going down when the pump is off? You get these kind of things, and something's wrong here with our data. And you've got to question it, because when you're working with data like this, trying to calibrate the model, the most fundamental rule is summarized by this little acronym: garbage in, garbage out. So you've got to really look at the data and question how good it is. Okay, so now let's look at how we calibrate the model. We've got our data now. We know why we're doing the study. We've got our data. So dry weather calibration, for sanitary systems is, adjusting the wastewater loading to meet the monitoring data. And for wet weather conditions, it's different between a sanitary system or a combined / storm system. You need to do some real hydrology. Well, sanitary sewer or rainfall-derived infiltration inflow is really tough to track down. The surface flow into sewers, though, with stormwater or combined systems can be traced back to more logical methods that are more scientific based rather than correlations, which you have to use for sanitary sewer inflows. Okay, so in general, the flows are, the behavior to model is very sensitive to the loading, how much gets into the pipe. And it's not that much as far as trying to figure out minor loss coefficients or friction. It's not that important in predicting flows. On the other hand, if you're trying to predict hydraulic grade lines in sewers, these become very sensitive to hydraulic properties or possible blockages in the downstream side. So dry weather calibration usually relies a lot on the water billing. This tells you where the customers are who are putting flow into the sewers. You want to get this data when lawn irrigation is the minimum. So there's some parts of the country where the difference in water use between summer and winter is really dramatic. So you want to get it during those times when people aren't watering their lawns. And so you compare this with the flows you're measuring, and just a matter of making sure you assign them to the right manholes. What you'll find, however, sometimes is the flow attenuation effects can make things a little bit weird. By that I mean this might be a typical water use pattern in a sanitary sewer or a combined sewer system in dry weather. And you have a morning peak and an afternoon peak, and they go down at night. And that's what you get. However, if you're working with a big enough system, by the time the flow gets there from the morning peak, it's already in the downward. From far away, it's already starting to drop close in. And similarly, at nighttime, when the water consumption has gone down, the flow keeps up because there's water that entered the sewer system 12 hours ago, 15 miles ago, and it takes a while. So that you tend to get a much more dampening in the data than you would have with the actual nodal loads that you put on. As far as looking at depth in these sewer systems, usually you'd like to see something like this, where the hydraulic grade is that blue line, and it's pretty easy to measure, and it's pretty uniform. Now, what happens is some cases you're going to have some odd flows. You're trying to figure out why is the hydraulic grade line so high at this one location. Something like this might be. And that's usually due to some kind of blockages, because the little errors in Manning's N aren't going to make a huge difference for the most part. So what happens is you might get something like this. So what you can do is go out there during the wet weather events and pop every manhole along the way. And if one of those manholes shows good flow and the next one shows a high flow, or if you're using something like chalking or cups or just some kind of depth logger, that'll tell you there's something wrong here. So now, what do? Do you adjust Manning's N or the pipe diameter to account for blockages, or do you fix the blockage? And that depends on what you're doing the model for. If you're trying to represent what's going on in the system right now, today, for real-time control, you actually try to simulate the blockage. On the other hand, if it's really something to do with a planning model, you want to tell them to get out there and unclog the blockage, and then we'll recalibrate the model for the real flows in the system. Now, one of the issues I have is something about poor pumping representation. What happens is with pump flows, you get some shifts in peak. When the pump cycles, the pump is on in the real world and off in the model, it may make the model look bad, but the flows are different. If the peak flow and the off periods are about the same and the flows are about the same, you shouldn't get too worried about that, as long as you're getting the right total volume of flow down the line. So you might see something like this, where those pumps they look like they're really terrible. We did a correlation coefficient between these two flows that you measure in a sewer, and you've got a pump station that's a little out of sync upstream. You might say this is a terrible calibration, and really it may not be all that bad, as long as the same volume of the curve is right. But dry weather flows and pump flows aren't that hard, really. The hard part are wet weather flows and stormwater flows. Okay, so the formula is simple. You have precipitation, then something happens, and you get flow in the pipe. And how you get there from one to the other is where the art of this comes in, and where the real work comes in. Now, The difference here is sanitary versus combined sewers are going to be very different, and they're different in a lot of ways. And I'll lump stormwater systems in with combined sewers. Okay, so in terms of volumes, in sanitary systems, the wet weather flow is more than the dry weather flow, but not hugely different unless you've got a bad system. While in combined systems, of course, the wet weather flow is hugely larger than dry weather flow. And in stormwater, of course, it's infinitely larger. And then there's the regulatory reason. Why are we doing these? Where's the issues? Like in sanitary systems, you're not allowed to have overflows. They're not permitted in your permits. While in combined sewers, they are permitted. You have overflow points that are permitted CSOs. So there's a little different emphasis in regulatory issues. And in hydraulics, in sanitary systems, you don't know where the infiltration inflow is coming in. If you did, you could fix it. While in combined sewers, you know where the inflow is coming in. You've got catch basins and inlets, and that's where it goes, in the gutter into the catchment basin. So there's a big difference between these flows that are driven by I&I versus those that are driven by typical hydrology. And so in terms of modeling and model calibration, usually we rely on things like the RTK method, which I'll talk about coming up, for sanitary I&I. While in combined sewer systems, you've got a lot of methods available that are based on much more logical and sound hydrology. So let's look at sanitary sewer hydrology. Okay, so where does the water get in? Well, you've got sump pumps in houses, you've got roof drains, you've got cracks in the pipe, you've got infiltration at manhole, you got the water table above the pipe. All of these are possible sources. And the problem is none of these are metered or known. And you're going to have to come up with a hydrograph that describes this. This is what you're looking for, some kind of hydrograph. And this is the shape of a typical unit hydrograph. This is a SCS unit hydrograph. You want to try to approximate it logically. Okay, so the method that a lot of folks use is called the RTK method, which takes that hydrograph, breaks it into pieces, and tracks them with three different parameters. One we'll call R, which is the relative flow to get into the pipe per unit of precipitation, which controls the peak of this hydrograph. There's the second thing in RTK is T, which is how long does it take to get to the peak. And the third one is K, which is how much longer is the recession leg than the rising limb. So those are the parameters. So that doesn't look too hard. You only got three parameters to adjust. So let's look at those parameters in more detail. So R is the fraction of rain entering the system. If you have a tight system, R is down near 0. Or if you have essentially a combined sewer, or if you want to use this for a stormwater system, which you wouldn't, it'd be 1. So you're going to be somewhere between 0 and 1, hopefully small numbers like 0.05 or 0.1. T is the time to the peak. Well, the peak is equivalent to the time of concentration, more or less, and it's something that you can adjust. Okay, so it's how long does it take for that rainfall to start to peak. And then K is usually just the ratio of how long the recession is to the rising limb. And in general, this is a number like 1.5 to 2 or something along those lines. So it's not too much fun to play with K. Now, how does this work? Well, this is a special type of system where you're basically superimposing different triangular hydrographs, including those three parameters. But the thing is, if you just try to make one hydrograph for a catchment, it doesn't work as well because they're different kind of processes. There's rapid inflow, which are people who have a catch basin hooked up directly into a sanitary sewer, for example. Then you have infiltration, intermediate level infiltration inflow, possibly sump pumps or something of that sort. And then you have this long-term slow infiltration. So there's really three types of these triangular hydrographs. So what you do is you add them up, and when you put them together, you get something that looks like this. Take the three of them, the rapid, intermediate, and slow, and they make a reasonable shape hydrograph. And you have a lot of adjustments you can make to make this work. Of course, having a lot of adjustments means there's more thinking you have to do. And in this case, you have to adjust those RTK coefficients. So in leaky systems, you have a large R value, or a lot of sump pumps, roof gutters, legal connections. Your R is going to be big. Okay, T is how big the catchment is. Now there's some question there. Okay, if I have a lot of rapid inflow, do I split that up between the first and the second and change the R rates, or do I just change the T rates? So there's some finagling have to do with the numbers here to figure out which is the best thing to adjust when you have something that's kind of like an intermediate level inflow. But it has units of time. The other things don't have units. This is the other one has a unit of time. And then there's K, which is that downward receding limb of the hydrograph. Okay, so you put them all together. And the other thing you got to watch out for, though, is that in the large pipes, you have flow attenuation. This is what the models can account for to use dynamic wave routing. And you have a lot of things that can cause these things to slow things down. But sometimes you really do have uneven flows. Sometimes you get odd things. You may have industries, for example, that do batch dumps of something. They may have some tanks that keep them full all day, and then at a certain time they dump the tanks. And you're going to get these weird shapes, and it's not going to fit RTK hydrographs or typical dry weather sanitary flows. And then you could look at incorrect pump cycling. Sometimes you have wrong pump curves in there, or wrong shape of your wet well that becomes the issue. Then you look at the components of the hydrograph. You have usually some kind of domestic load or no load in stormwater systems. You have rainfall-derived I and I in these systems, and you have base flow. Now, what is the base flow? There's some people that say you've got to have a pretty big base flow for that nighttime flow when no one's using the water. And other people say, well, base flows really should be absorbed. It's just really rainfall, and it should be absorbed into the hydrographs. Well, it really depends. Okay, so we look at this. We have the green is the domestic load, the blue is the stormwater event, and the red is some type of base flow. What does it look like? Well, it really depends on your hydrology, and it's not one number for the whole system. You can't use this, how many gallons per day per foot of pipe length or something like that, because it depends on some parts of your system. The water table is going to be well below the pipe, in which case the pipe is sitting in dry ground, and unless you're having immediate rain with a lot of leaks, there's going to be no base flow. It's just going to be non-existent. Then you have some where the water table is up around the area of the pipe elevation. So here you're going to get some infiltration over time, but it's not going to persist very long. It's going to be much more like the slow infiltration part of an RTK hydrograph. And then you have the kind where the sewers are below the water table. And this, you don't like this one, but they exist. If you're alongside a pond or a river, or if you have a water main leak in that area that's been leaking for years and no one's detected it, you're going to have saturated ground above it, and you're going to have a lot of base flow. So this is going to vary through your system. So in that upland area where you don't have a high water table, you're going to see that as soon as it gets done raining, this dies off pretty quick. If you're near the water table, it'll take a lot longer, and you will have a significant base flow possibly. And if you're in an area where you've got a pond right next to the sewer, it's going to stay that way all the time, and you do have a significant base flow. So in some cases, the base flow is something you separate out. In some cases, it's just part of the hydrology of the system. How do you enter this data? Well, it depends on how the software you're using. Here's one place where you put the RTK coefficients in, and this is another way in another model. I won't get into the details of which model, but there are basically dialogues where you just fill in the numbers. Now, some of these you can actually change those coefficients by month of the year, even if you want. And then the next thing is, what do the catchments look like? Because remember now, you're applying this to a catchment. We're talking about inches of rainfall, but it depends on how big the catchment is. And nowadays, we've come a long way in catchment delineation, where in the old days, you'd have to sit there to topo map and try to draw the boundaries of each catchment. Nowadays, you basically click on, do some catchment delineation for me, and it will spit out the catchment delineation. So you see where the water gets into the system at, and how much is each entry point related to the catchment size. But now you get to the question, we're going back to why are we doing this modeling in the first place? Okay, so if you're calibrating the model, and we're talking about calibration here, do you need to, this is the case, we have 6 little catchments, and I got a flow meter downstream of those 6 catchments. Okay, all you can calibrate at is that node J6. You really can't do much to say whether the inflow is coming in through 1, 2, 3, or 4, or 5, because you don't have any data to prove it. So if your model is only one you're going to be using for downstream studies of overflows, you really could start your model at J6 and use one big catchment. On the other hand, if this is a place where you're going to be tying in a new subdivision up above, and you really need to know the details, your model needs to be calibrated up above. You may need to put in some temporary flow meters even. So our goal again is to capture the flows, both the dry weather and wet weather flow, to make that magenta hydrograph. So now we get to the combined sewer and stormwater systems, where you have precipitation, and we know the process is a lot better. These have been studied in hydrology quite a bit. You have precipitation, you have depression storage, infiltration, runoff to the sewers, and so it's the processes are known, and you know where the inlets are. So you have a much better chance of doing a better job of calibration if you want to get down to the details. So you load the model with the catch basins. Okay, so that's pretty easy. A big thing here in this type of situation is pervious versus impervious, because it makes a huge difference in the amount of water that gets captured and also how much gets seeped into the deep groundwater as opposed to running off, and how fast it runs off. But there's a lot of methods available. You think that, well, we'll use the theoretically correct hydrograph method. Well, catchments aren't that simple. You've got pavement, you've got green spaces, you've got rooftops, you've got hills, you've got the flat areas, you've got a whole variety of places, things that can happen. So these models, even though they're very theoretically soundly based, still are hard to calibrate because there's so much that goes on. You're not going to be doing every little low spot in people's backyards and such to account for storage. So it's going to be tough to get it really precise. But there are methods though here that are rationally based, which is really good. So you have some advantage in doing stormwater modeling. Then it's a matter of delineating the catchments that go to each catch basin, and there's software out there that will do that. It'll show you where you put the catch basin down. You've got the terrain model, and it'll say, okay, this catch basin gets that green area, and the next catch basin up gets that magenta area. So you can do really precise modeling if you want. This is especially good when you're doing stuff like road design, for example, or subdivision design, where you can, we don't yet, this is now before you get the calibration, but you can also do this after calibration when you have good drawings of what the topology looks like, what the topography rather looks like, where the slopes are. You can really nail the amount of inflow at each location, and the gutter shapes and such. Okay, so just another word about force mains and pump stations. If you have them, you usually have good data there. It's one of the places in sewer systems where they do collect a lot of data, or in the level of the wet well, the flow, the discharge pressure. So you should be able to calibrate your model pretty well. Some of the problems that you deal with are the pump curve is no longer right, or it never was right. It's the wrong pump curve. You need to find that original pump curve. And that sometimes takes a good bit of work because they got the pump curves and the pump was installed, and you come in there and ask for where that pump curve is, and they say, oh, Charlie used to keep those in a drawer on the right-hand side of his desk, but he retired in 2012, and I don't know what they did with his old files. Where are his old files, And so you have some of those issues, and then you also have to learn about how the pumps are controlled. If they're controlled off of a typical remote control of the pump station itself controls itself. It's not controlled by a main control room. And usually there's nice settings for the on level for the first pump, the off level for the first pump, the second pump's on level. The problem you could have in force mains, though, is if they don't have air release valves that are working. If they're blocked, you can have restrictions in the flow if you have either a high point without an air valve or one that is a clogged air valve to look at. As I mentioned earlier, the total flows should match out of pump systems. It should be pretty accurate, but the timing is tough to get. You're not very going to get that quite exactly right. And when you have multiple pump stations in a force main, this gets to be pretty interesting, especially their variable speed pumps, because they tend to fight with one another for the capacity of the system. And this gets to be kind of a fun challenge to deal with. Now, getting away from the specifics and the details of calibration, let's talk a little bit more about Zen and the art of calibration. You got to be careful what you adjust, because one of the terms I've coined is calibration by compensating errors, where if you have an error in one parameter, if you make an error in another parameter, you can kind of cancel each other out if you're not careful. So if you have the wrong catchment area and you put in a wrong SCS coefficient, let's say, they might cancel each other out. Or if you put the wrong Manning's N in to account for the fact that you really had blockages in the sewers, that could account for it. The problem is, if you do this for one set of data, you might be able to get away with it. But if you try to validate that model against another set of data, it usually doesn't work very well, because that compensating error thing only works for one data set. If you have two data sets, it's hard to make the same compensation right. So you've got to be very careful that you're adjusting the right thing, which goes back to the question I asked earlier, is why is your model not calibrated in the first place? So it's important to understand the adjustments. Don't just blindly make adjustments so that you match the outflow hydrograph. Are you making reasonable adjustments? Are there special circumstances where you're out there calibrating the model at a time when, let's say, there's a big construction project going on and there was a lot of runoff from the construction site, which shouldn't have happened? Or was this during spring break at the university and the dry weather flow component of the combined sewer flow was nil because everybody was on spring break? Or is there unusual loads? Were there blockages in the system? So understand, why are you making these adjustments? Maybe you collected the data and you thought that the data was collected in the middle of the day. You still can't use 0 as a starting point. You don't know what time of day was this. Are the sanitary loads and the wet weather loads additive, or are they different times of day? Okay, now we get even more into these philosophical discussions as what is good enough for model calibration? Well, or when are we done is the other question. And the trouble is, you're never done. Systems are continuously evolving, and you're getting more and more data in. So, calibration isn't quite ever done. Now, of course, and then why are you using the model? The model may be very good for one purpose, but if you use it for another purpose that it wasn't dependent on, you may need to go back and do some recalibration. So the more work you can do, the better. The more you calibrate the model, the better your model will be. But it's hard work and costs money, as I mentioned earlier. So you've got to be careful. Initial calibration, though, is required. If you're going to build a model, you really need to do that initial calibration. And then later, it's much more of an issue of validating it as you get more and more data. Now, I still haven't answered, when are we done? Okay, what's good enough? Okay, so to do that, though, you need to understand the roles in model calibration. One role is that of the modeler, which is probably you. You build the model, you got the data for calibration, you made the comparisons, adjusted the parameters, and you've done your job in calibrating the model. But there's another role in modeling, and that is the person who uses the model, the results. Now, you may be running the model, but it's somebody else is possibly the design engineer for the project or the senior operator of the system who is the user, the decision maker. And he relies on the model for decision support. So, when is the model calibrated? Now, what usually happens is the user comes up to the modeler and says, is this model calibrated? And you're supposed to give a yes or no answer. And I think that's the wrong way to do it. What should happen is if somebody says, is this model calibrated? You say, here's what I did to calibrate it. Do you think it's good enough? It's the person who's got to sign the drawings, or this licensed operator should be the one who decides if that model is good enough. And you, as the modeler, should provide them with enough information to demonstrate that it is good enough and show them what the limitations are as well. And it's that interaction between the user and the modeler that I think really needs to be understood. Now, you may be one person who's the modeler and the design engineer. That's possible. But the modeler could be a contractor that you hired, and the user is somebody in-house, or vice versa. You have an in-house guy building the model, but they give the model to the consulting engineer to do the study. So, this could be one person. It could be two companies. It could be two consultants. But the thing is, there are two roles, and it's the person who makes the decisions who really should decide, is this model calibrated well enough, or do I have to go back and do some more calibration? So when is the model good enough? Well, we talk occasionally about stupid standards for model calibration, and I just don't think that's really possible. Anytime someone's come up with a standard for model calibration, I can shoot holes in it. Do some sensitivity analysis where you play with some of the parameters and see how they affect the model result and see what's important. The goal really is to support the decision-making process. It's so that the model user calls you up, the modeler, and say, hey, what does your model say about this? So the real rule is stop your calibration when the cost to do additional calibration exceeds the benefits. That's the real rule as to when you're done with model calibration. So to summarize this whole thing, we've talked about what is calibration, how to approach calibration, what kind of field data you have, identifying why the model's not calibrated, correcting it, and then trying to decide if we're done yet. And if you're not done, well, you got to go back where that guy in the picture is and keep working. So thanks a lot for listening to this, and I hope you found it useful. My name is Tom Walski at Bentley.com if you have any questions about it. So thank you, and hope you have a good day.